Given the vector field f defined by e to the minus 2x z cubed minus 2x e to the minus 2y and 3y plus 1 z squared, prove that it is a conservative vector field and find its potential function. So when you're dealing with three-dimensional vector field, to prove that you're dealing with a conservative vector field, meaning that it is the gradient of function f, which in that case is called the potential function. It means that the curl of f is the irrotational. That means that it's the zero vector. So remember, for the curl of f is defined as the determinant of the matrix with entry ijk. Then this is the partial with respect to x, this is the partial with respect to y, this is the partial with respect to z, and then the last entries are the components of the vector field, which are e to the minus 2y, z cubed minus 2x e to the minus 2y, and then 3, I need more space here, times y plus 1 z squared. And then I'm going to use the method of repeating the first two columns and use the products of diagonals and antidiagonals to find this determinant. So let me rewrite this. And also remember, this is the same thing as the cross product of the gradient with the vector field. So the first diagonal here is the partial with respect to y of 3y plus 1 z squared. 3 and z squared, when it comes to the y variable, is really just a constant. So it's really like the 3 and the z squared. And so you just take the partial derivative with respect to y plus 1, which is 1. So you get 3z squared I. And then you look at the second diagonal, is j times the partial with respect to z of e to the minus 2y. Well, there's no z here, so it just e to the minus 2y is just a constant when it comes to the z variable. So that means that you're going to get 0 when you take its partial derivative with respect to z. Then the last diagonal is k times the partial with respect to x, z cubed. When it comes to the x variable, z cubed is treated as a constant, so its derivative is 0. Minus 2x to the negative 2y. The 2 and the e to the minus 2y are treated the same way when it comes to the x variable, because they are both constants. So it's just taking the derivative of x, which is 1. So it's going to be minus 2e to the negative 2y k. And then we're going to look at the anti-diagonal. So it's going to be k, so it's minus k. Remember, we negate the anti-diagonal. The partial with respect to y of e to the minus 2y, that's a fairly straightforward chain rule. That's going to be negative 2 e to the negative 2y. Then minus the second anti-diagonal, which is I, times the partial with respect to z of z cubed, which is 3z squared, and the partial with respect to z of negative 2x to the 2y, negative 2y, because there's no z variable, this is just a constant, and the derivative of a constant is 0. So that's finished. And the last anti-diagonal is the minus against minus j times the partial with respect to x of 3 times y plus 1 times z squared. There is no x variable, so all of it is treated as a constant. And then when we put everything together, the I component is 3z squared and minus 3z squared, they cancel. The j components are both 0, so that's good. And here's minus becomes positive, 2e to the minus 2y for the k component, and here we have negative. So that means here the curl is the 0 vector. Everything cancel each other out. So f is conservative. So that means that it's going to be the gradient of some function. So that means that the vector field, which is the vector e to the minus 2y, z cubed minus 2x e to the negative 2y, 3 times y plus 1 z squared, is the gradient. And remember, the gradient vector is the vector that has for component the partial derivative of the function. So it's going to be partial with respect to x, partial with respect to y, this partial with respect to z. So that means this is equals to the partial with respect to x. And so, right, those are equal. And this means this and this are equal, so that means that the partial with respect to y of that potential function, which we know exists, is equals to z cubed minus 2x e to the negative 2y. And finally, the last component, which I should write it a little bit better because it looks like a parenthesis, is equals the partial with respect to z. So that means that the partial with respect to z is equals to 3 times y plus 1 z squared. So we're going to do the method of integrating each of the partial derivative with respect to the proper variable. And remember what we mean, that would be we will obtain the function, the potential function f of xy, but from a different perspective, and we'll put together everything to actually figure out what the function is. So if we integrate, so here we know the partial derivative with respect to x. So to undo the derivative, we're going to integrate, but here we integrate with respect to x, e to the minus 2x. So if you integrate e to the minus 2x, again, this is a simple one. It's e to the ax when the entire derivative is 1 over e to the ax. So a here is negative 2, so it's going to be negative 1/2 e to the negative 2x plus a constant, but when it comes to the x variable, any function of y and z are constant. And then we're going to do the same thing for each and every one. So we're going to integrate here with respect to y because we know the partial derivative with respect to y. To undo that, we're going to integrate with respect to y. So if you integrate z cubed with respect to y, you get z cubed y. If you integrate minus 2x e to the negative 2y with respect to y, so remember when it comes to the y variable, 2 and x, which are multiplying the function of y, I treat it as a constant. So we leave that constant, and we're going to integrate with respect to y e to the negative 2y. And similarly here, as we did, the antiderivative e to the minus 2y is going to be negative 1/2 e to the minus 2y plus a constant, again, but when it comes to the y variable, both x and y treated as a constant, so plus a function of x. So I'm going to rewrite here. So again, remember that what we did here, we partially recovered the potential function. So again, I'm going to write this. So here minus become positive, 2 and 2 like cancel, so it's going to be x e to the minus 2y plus a function of x and z. And last, we're going to use the last partial derivative, which was the partial derivative with respect to z. So to undo that, we're going to integrate that whole function with respect to z. So when it comes to the z variable, y plus 1 is used as a constant, similar to the 3. So it's going to be 3 times, again, a constant times z squared, sorry. So by the constant rule of multiplication, constant rule, you keep the constant. So again, 3 and y plus 1 are treated as a constant, and then you integrate the function of z, which is z cubed over 3 plus a constant. But when it comes to z variable, x and y are constant. So here, if I were to just look at the partial with respect to z, I partially recover the potential function, and I find, so the 3 cancel here, to be y z cubed plus z cubed plus k of xy. So now I'm going to zoom out. So you must realize that this 3 expressions are the expression for the same and unique function f. This is the same function, just viewed from different perspectives. So think here is when we partially recover by looking at from the x direction. So let's say that means we were looking at the depth, and we see that what we recover was, and basically the other view, the y and z view, are obstructed. So if I only look at the object from the x direction, the only thing I can see is negative a half e to the minus 2y. And then oh, sorry, I actually did not realize, I apologize here, I just made a mistake. This is e to the minus 2y. When I rewrote it, I wrote x. So that change here, I apologize for that. This is e to the minus 2y. I just wrote it wrong when I was doing it. So here, that means this is wrong. Let me just redo that part. So here, we integrate e to the minus 2y with the x variable. With respect to the x variable, e to the minus 2y is treated as a constant. The antiderivative of a constant with respect to x is that constant times x. So sorry, I just rewritten wrongly my function. So what I said earlier still stands. If we were looking at from only the x direction, meaning the y and z directions are obstructed, I see that my potential function, or my object, is x e to the minus 2y. Now I'm looking at from the y direction. That means kind of x and the z direction are obstructed. And I see that my function, or my object, is z cubed y. Well, z cubed y, I could not see that from the x direction. You see, this is when we look at for the x direction, because the y and the z direction are obstructed. Anything with the y, only y and z, I cannot see it, and that is the thing I cannot see, the z cubed y. And then x e to the minus 2y, well, here that is a common part of the object, that if I look at from the x or the y direction, that part of the object is not obstructed. So, and I don't repeat it because I already actually seen it from the x direction. And now finally look at from the top, like think about if z is the height, from the top direction, then we see the function that we partially recover is yz cubed, which actually I could see it from the y direction. I could see that part of the object z cubed y, so I don't need to rewrite it. But the z cube here is solely a function of z. So if I look at from the x and from the y direction, I could not see it. So I need to add it to my potential function. And then function of y, z, x, z, and x, y, any constant is going to be actually a function of yz or xz or xy. So this is the most common form of the, or the most general form, not common, of the potential function. And then you can always check, because if I were to differentiate this function with respect to x, I should find e to the minus 2y. If I differentiate this function with respect to y, I should get z cubed minus 2x e to the minus 2y. And if I differentiate with respect to z, then I should get z cubed y plus z cubed, which is 3y plus 1z squared.